Hi guys, welcome to our last section of this exponential function unit. We have talked all about exponent properties, and we have talked about then some different applications, including scientific notation. We've talked about what a normal graph looks like. We've talked about exponential growth and decay, and we've talked about sequences. So today what we're going to do is we're going to take a step back to the graphing section a little bit, and we're going to look specifically at how numbers can change what the graph looks like. So hopefully you have been able to print this worksheet that was posted today. If you weren't able to print, you can just go ahead and kind of follow along on paper as we go along. This is going to be kind of just an interactive lesson, not really a lot of homework, just something that we work on together. All right, so the first thing it says is opendesmos.com, and I'd like for you to go ahead and do this with me. Opendesmos.com, and we're going to graph the function f of x is equal to 2 to the x power. And then we're going to sketch the graph here on our page. They ask us to take note of a couple of things: x-intercept, y-intercept, and the shape of the graph. So I'm going to come up here to Desmos. This is what we should look at. You might have to hit the graphing calculator button. And then we're going to type in f of x is equal to 2 to the x. Now you can type in the f of x if you want, or you can type in y. Remember, f of x is just another name for y. So y equals 2 to the x power. Now, in order for me to get the exponent button, you're going to come down here to my to this keyboard button, show the keyboard, and our exponent button is right here, a to the b power. So we're going to type that and get our x in here. And so this should look familiar. This is what we have talked about before. So we were supposed to take note of a couple of things. X-intercept, if you'll remember, this graph is never going to touch the x-axis, so there is no x-intercept. Y-intercept, remember it's normally at 1, unless we have that a value in front, and in this case we don't. So looking at my graph, I see that it does cross here at 1. I know it looks kind of like maybe that's at 2, but if you look at it, looks like each of these markings is a half. And then the shape is that exponential curve that we are used to. So I'm going to come back now to our graph, and we're going to draw a quick sketch of what this looks like. And so again, no, not going to cross the x-axis. It's going to be really close there. It's going to cross at 1, and then it's going to be that nice curve. All right, so that's what our basic exponential function looks like. Hopefully that's a little bit of review. And they ask, is the relation a function? And so if we remember a function, when I look at a graph, we can use the vertical line test, and this one does pass the vertical line test. I can draw those vertical lines and they only touch once. So it is a function. And another hint here, guys, is when I see this f of x, that tells me that this is a function. All right, so what we're going to do today is we're going to look at what effect adding and subtracting numbers in different positions has on our graph. We already know that when we put a number in front by multiplying, that changes our y-intercept. But now we're going to look at what happens when I add or subtract numbers in different places. So the first one we're going to transform, that just means move, is we're going to do 2 to the x plus 3. All right, so I'm going to come back up here to Desmos. And I'm going to leave that 2 to the x here. Let me go ahead and erase my markings here. I'm going to leave that 2 to the x there so we can compare. And I'm going to start a new line where it says I'm going to now graph y equals 2 to the x, so 2, and then come down here to the a to the b, x. And then I'm going to need to arrow out of that to get out of the exponent to say plus 3. And so I want to take a minute and just take a notice of what happened when I did that plus 3. Does anyone notice about my y-intercept here? I changed. I was at 1, and now my y-intercept is at 2, 3, 4. So it was at 1, now it's at 4. Does anyone see that I've taken that whole graph and just shifted it up 3 units? So where it was flat here on the X, now you can see it's flat here almost at the 3. Interesting. Let's try the next one. The next direction says, take a look at what happens when I graph 2 to the X minus 3. So I'm going to again type in y equals 2 to the X power. Again, I'm going to arrow out of that and then say minus 3. I'm going to shut down my keyboard here so we can see a little bit more clearly. Do you see how this one has now shifted the whole graph down 1, 2, 3 units? Again, it just pushed that whole graph down 3 units. So when we come back to our worksheet, you can do a quick sketch of those. Remember, it's now crossing up here at the 4. So it's not crossing at the 3, it's crossing at the 4 because I've shifted up 3. And remember, it was crossing at 1. So up 3 means I'm at 4. And this one has shifted down 3. So it's going to cross down here at negative 2 and look something like this. So when I come down here and look at answering my question, the question says, how do these compare with my normal graph? We're going to say adding or subtracting. Adding or subtracting moves the graph up and down. Adding moves it up, subtracting moves it down. All right, now we're going to move into the next portion. So it says, now let's consider f of x equals 3 to the x. All right, so let's try this. So I'm going to erase all of these that I've done because I'm going to do something new here. So now I'm considering the graph f of x equals 3 to the x. So y equals 3 to the x power. Okay, so we see that. Now, what do you suppose is going to happen if I do a plus 1 on this 3 to the x? I hope you noticed and said, well, because we're adding 1, it's going to shift the graph up 1. So let's test that hypothesis and see if it's true. So y is equal to 3 to the x power, and then I arrow out of that and say plus 1. And if you'll look at this, that is exactly what happened. It moved and shifted it up 1 unit from the original. All right, and then it asks me to consider what will happen if I take 3 to the x minus 1. Again, take a guess on what you think will happen based on our previous knowledge. Let's test it out. Y is equal to 3 to the x power, arrow out of that, minus 1. And again, you can see from that original purple graph, it's shifted the whole graph down 1 unit. So what happens to the original function? Again, when I add that number at the end, it looks like it shifts up and down. Addition looks like it shifts up. Subtraction looks like it shifts down. All right, so these next ones now, we're going to look at something different. So back at our on our paper, this one says, now consider f of x equals 2 to the x. So we're going back to the original graph that we have done, and it says make a quick sketch of that graph. Now again, if you'll remember, we've done this one before. X-intercept, remember, it doesn't have an x-intercept. It crosses the y at 1. And then its shape is that nice exponential curve. We've already said that this is a function because it passes the vertical line test and because of this hint, f of x. We're going to do a different type of transformation this time. This time we're going to input g of x equals 2 to the x plus 3. If you'll notice that x plus 3 is part here of our exponent. So when we come back to Desmos to do that, so let me go ahead and get rid of these problems that we've done. I'm going to put in our original function again. Y is equal to 2 to the x power. And then I'm going to try this y is equal to 2 to the x plus 3 power. Now, here's something interesting that happens. If you'll notice, that plus 3 did not stay up there in my exponent, and so when it jumps down, it's doing just what we have done before, and that's not what I'm looking for this time. This time, I want the plus 3 to stay up there in the exponent. So in order to get it to stay up there in the exponent, when I hit my exponent button here, I'm going to need to use parentheses to keep that x plus 3 all as part of the exponent. And I put an equals in there, but I'll fix it. Now I'm at plus 3. Okay, so something different happened this time. This time it didn't move up. But again, if we look at that y-intercept portion, we can look and follow that. It looks like 1, 2, 3. It looks like in this case, the plus 3 made it move to the left 3 units. Can you see that? That I just took the graph and shifted it over to the left. All right, the next one says, then how does it compare to j of x, which is 2 to the x minus 3? So let's try that one and see if we can see something that's happening there. So I'm going to try a new one. Y is equal to 2 exponent. And then again, I'm going to need parentheses this time because I want that all to stay up there as part of the parentheses. So x minus 3. And you'll see then that purple graph, it seems to move to the right. 1, 2, 3. So when I compare these, or when I think about these, this seems a little bit backwards. It seems to me that plus 3 should move to the right and minus 3 should move to the left. Just like in the previous problems, plus 3 moved up and minus 3 moved down. Guys, this is something I like to call the Spider-Man principle. And I know that this seems a little silly and you may think, why are we talking about Spider-Man in the midst of these problems? But this is something that I learned quite some time ago, and it's helped me kind of keep this straight, even when it seems backwards. And so let me introduce to you what the Spider-Man principle is, or the way it helps me remember. When I think of Spider-Man, most of the time when I picture Spider-Man, I picture him hanging on the side of a building. Because Spider-Man was created to do something special that the rest of us can't do, and that's climb up and down the outside of a building. And so when I add a number to the outside of an equation, for instance, y is equal to 2 to the x plus 3, when I add that 3 to the outside of the building, Spider-Man is on the outside of the building and does just what it says. So plus 3, he goes up 3. If it was minus 3, he goes down 3. So when that 3 is on the outside of the building, he does exactly what it says, up and down, just like he was created to do. However, when those numbers are inside the exponent, they're trapped. And so in this case, when I look at y is equal to 2 to the x plus 3, that 3 in this case is trapped. So think about it in your own room or in our classroom. If Spider-Man were on the wall in our classroom, there's really not space for him to go up and down, or at least not much, because there's a floor and the ceiling in the way, unlike on the outside of the building where he's free to do that. So when he's trapped on the inside of a building, he can't go up and down. He has to go left and right. But see, Spider-Man wasn't created to go left and right. He was created to be on the outside of the building going up and down. So when he's inside and trapped, he's angry and he goes the opposite way the sign says. So when it says +3, he doesn't go to the right 3, he actually goes to the left 3. And if that same problem was 2 to the x minus 2, we would think he's going to go to the left 2, but he actually is going to go to the right 2. So these are the two ideas that I want you to think. When we add or subtract a number outside at the end of the problem, he's going up and down and he follows the way the sign says. But when we add or subtract a number inside the parentheses, he's trapped and he must move left and right and he goes opposite the way the sign says. So let's look at this next problem. This next one says, so consider f of x equals 3 to the x. Remember, that's just a normal exponential curve. It does not have an x-intercept. It crosses at 1 at the y-intercept and then follows our normal curve. So what will this problem do? When it says f of x, g of x, is equal to 3 to the x minus 1. So where is that minus 1 located? Is it out free on the outside of the building or is it trapped on the inside? Even though we don't see parentheses, it's trapped because it's part of the exponent. So because it's trapped, that means the transformation is moving left and right. And because it's trapped, we go the opposite way we think. So instead of now me crossing at positive 1 here, I'm going to go over 1 and cross at the positive 1 over here. But the shape of the curve is the same, and so it's still going to be that nice flat line. It's going to curve up and touch through there and then be our nice curve. All right, next one. What happens when it says +1? Again, we need to look, where is the +1 occurring? That +1 is occurring when it's trapped. And so when it's trapped, that means we're moving left and right. And because we're moving left and right, Spider-Man's angry and he goes the opposite way. So instead of crossing at the y-intercept of 1, we're going to move that y-intercept over 1 to the left. And our graph is now going to look like this. It's just going to curve a little bit earlier. All right, so let's take a look. You can use Desmos to help you as you do these next few problems, just to kind of check. But can you predict how f of x equals 3 to the x minus 5 compares to g of x, which equals 3 to the x plus 3? So again, we have to think a normal curve, what would it do? And then what would this minus 5 do? Because that minus 5 is on the outside, Spider-Man is free to move. That means it would move the normal curve down 5. But then what would this one do? That plus 3 is on the outside, so it would move the normal curve up 3. So what's the difference between these two? It would move f of x up 8 units. They would be 8 units apart because we would take the normal curve and move it down 5, and then we take the normal curve and move it up 3. That would mean they are 8 units apart. Okay, next one. How can we predict how f of x equals 3 to the x plus 2 compares to f of x equals 3 to the x minus 7? Well, f of x equals 3 to the x plus 2. That plus 2 is trapped. So I'm going opposite direction that I think it should go. So I'm going to move. This one's going to move to the left 2. The minus 7 on this one is trapped again. So it's going to make it move to the right 7. So how far would these be apart? It would move from f of x. We would move f of x 9 units to the right to get g of x. All right, continuing. Now we're just going to use some of our thoughts. So it says, look at our original function of f of x equals 4 to the x, and then describe these changes. So all we're going to say is up, down, left, or right, and then how many units. So on this first one, the 9 is trapped. That means left and right. And because he's trapped, he goes the opposite way we think he should go. So instead of going to the -9, he's going to the +9. So that would be a right 9 units. Okay, part B. Where is the 9 located? It's located outside. Spider-Man is happy when he's outside the building, so he does what it says. He's meant to go up and down. So this one, because it's a minus, we would go down 9 units. Okay, the next one, number 2, says look at the original function. F of x equals 8 to the x power and describe the changes. Ooh, this one's a little more challenging because we see numbers in 2 places. So start with the first one. That -4 is trapped. So when the number is trapped, we're moving left and right, and we go the opposite way we think it should go. So it's going to the right 4. But then we also have this +5. The +5 is outside the building. It's not trapped, so it's going up 5. So we're doing both of those things. All right. The next one says h of x is equal to 8 to the x plus 3 and then -7. So again, the +3 trapped. We go opposite the way we think it should go. So this one's going to the left 3. And then the 7 is outside and free. He goes just the way it's supposed to. So we're going down 7. All right, last but not least, now we're going to write our own equation doing these certain things. So we're using the parent equation or the basic equation, f of x equals 4 to the x power. And so it wants us to move up 4. So we need to think, if I want to move up 4, do I want my 4 to be trapped or do I want it to be outside the equation? And up and down is when Spider-Man is outside the building. So we're going to write 4 to the x plus 4. And that would be f of x equals, or g of x, or y, or whatever. Okay, if I want to move to the right 4, remember right and left is when that, or right 8, I'm sorry. Right and left is when we are trapped, and so we want the 8 to be part of the exponent. If I'm going to move to the right 8, though, remember it's backwards, and so I want the 8 to be part of the exponent, but I want it to be subtraction. Part C, if I want to move down 6, down is when we're outside the building. So we're just going to say y is equal to 4 to the x and then -6 out there outside the building. And finally, part D asks us to do 2 things. It asks us to move to the left 4 and up 3. So we'll start with the left 4. Left and right means we're part of the exponents and we're going the opposite direction. So left 4 means I would want to take x plus 4. And then when it says up 3, that's going to be outside. And I'm going to say plus 3. Guys, just to sum this up, transformations is really just saying, let's look at a basic exponential function and see how adding and subtracting numbers in different places on that equation changes the graph. And so what we've learned is that when we add or subtract a number at the end of the exponential function, that has the effect of moving the graph up and down based on the number that you have there. So if it's a +3, it moves up 3. And if it's a -7, it moves down 7. However, adding or subtracting a number inside the exponent or as part of the exponent has the effect of transforming or moving the graph side to side, left and right. And it moves, again, the number that's there. The difference here on this one is that it moves the opposite direction that we think it should move. So when we see a +3, it actually moves to the left 3. And when we see a -7, it actually moves to the right 7. Guys, there's not an assignment on this. This is just something that I wanted you to be aware of. I wanted you to see. We're going to see transformations again in our next type of function that we're going to talk about. And so we will revisit this idea. Um, but I wanted you to be aware of that in this particular problem. I hope that makes sense, guys. We're going to begin reviewing for our next unit test. And so be on the lookout for some review sessions and things you can do to help yourself prepare. Again, thanks for stopping in. I hope this makes sense. And let me know if you've got any questions. Mr. Jordan and I would both be happy to help you out.